Double precision floating point format is a computer number format that occupies 8 bytes in computer memory and represents a wide dynamic range of values by using floating point. Computers with 32-bit storage locations use 2 memory locations to store a 64-bit double precision number. Double precision floating point format usually refers to binary 64, as specified by the IEEE 754 standard, not to the 64-bit decimal format decimal 64. IEEE 754 double precision binary floating point format, binary 64, double precision binary floating point is a commonly used format on PCs, due to its wider range over single precision floating point, in spite of its performance and bandwidth cost. As with single precision floating point format, it lacks precision on integer numbers when compared with an integer format of the same size. It is commonly known simply as double. The IEEE 754 standard specifies a binary 64 as having, sign bit, 1 bit, exponent width, 11 bits, significand precision, 53 bits, this gives from 15–17 significant decimal digits precision. If a decimal string with at most 15 significant digits is converted to IEEE 754 double precision representation and then converted back to a string with the same number of significant digits, then the final string should match the original. And if an IEEE 754 double precision is converted to a decimal string with at least 17 significant digits and then converted back to double, then the final number must match the original. The format is written with the significand having an implicit integer bit of value 1. With the 52 bits of the fraction significand appearing in the memory format, the total precision is therefore 53 bits per mil 15.955. The bits are laid out as follows. The real value assumed by a given 64-bit double precision datum with a given biased exponent and a 52-bit fraction is or between 252 equals 450359627370496 and 253 equals 9007199254740992. The representable numbers are exactly the integers. For the next range, from 253 to 254, everything is multiplied by 2, so the representable numbers are the even ones, etc. Conversely, for the previous range from 251 to 252, the spacing is 0.5, etc. The spacing as a fraction of the numbers in the range from 2n to 2n plus 1 is do now 52. The maximum relative rounding error when rounding a number to the nearest representable one is therefore 2 of 53. The 11-bit width of the exponent allows the representation of numbers with a decimal exponent between 10^308 and 10,308, with full 15 to 17 decimal digits precision. By compromising precision, subnormal representation allows values smaller than 10^323. Exponent encoding. The double precision binary floating point exponent is encoded using an offset binary representation, with the zero offset being 1023. Also known as exponent bias in the IEEE 754 standard. Examples of such representations would be, E mean equals a 1022, E equals a 973, E max equals 1023. Thus, as defined by the offset binary representation, in order to get the true exponent, the exponent bias of 1023 has to be subtracted from the written exponent. The exponents 00016 and 7ff16 have a special meaning. 00016 is used to represent assigned zero and subnormals. And 7ff16 is used to represent A and nans, where M is the fraction mantissa. All bit patterns are valid encoding. Except for the above exceptions, the entire double precision number is described by. In the case of subnormals, the double precision number is described by endianness. Although the ubiquitous x86 of today use little endian storage for all types of data, there have been a few historical machines where floating point numbers were represented in big endian form while integers were represented in little endian form. There are old ARM processors that have half little endian, half big endian floating point representation for double precision numbers. Both 32-bit words are stored in little endian like integer registers, but the most significant one first. Because there have been many floating point formats with no network standard representation for them, there is no formal standard for transferring floating point values between diverse systems. It may therefore appear strange that the widespread IEEE 754 floating point standard does not specify endianness. Theoretically, this means that even standard IEEE floating point data written by one machine might not be readable by another. However, on modern standard computers, one may in practice safely assume that the endianness is the same for floating point numbers as for integers, making the conversion straightforward regardless of data type. Double precision examples. 3FF00000000016 equals 1, 3FF00000000016 a per mil 1.0000000000000000002, the smallest number greater than 1, 3FF0000000000216 a per mil 1.0000000000000000004. 4000 equals 2, CO 100 000000016 equals a euro 2. 00000000116 equals to a 1022 a 52 equals to a 1074, a per mil 4.940656458412465 a 10 a 324, 000FFFFFFFFFFFF16 equals to a 1022 a 2 a 1022 a 52, a per mil 2.22507385850720009 a 10 a 308, 0010000000016 equals to a 1022, a per mil 2.22507385850720014 a 10 a 308, 7 FFFFFFFFFFFF16 equals a 21023, a per mil 1.79769313486231157 a 10308. 0000000000016 equals 0, 8000 00000000016 equals a euro 0. 7 FF00000000016 equals an FFF00000000016 equals AA. 3 FD 555 55 55 55 555,516 a per mil 1/3. 1/3 rounds down instead of up like single precision, because of the odd number of bits in the significand. In more detail, given the hexadecimal representation 3 FD 555 55 55 55 555,516, sign equals 0. Exponent equals 3 FD 16 equals 1021, exponent bias equals 1023, significand equals 555 55 55 55 555,516, value equals 2, exponent to exponent bias, 1 significand a euro. Note the significand must not be converted to decimal here, equals to a 2 equals to a 54 15 55 55. 55 55 555,516 equals 0.33333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333. A per mil 1/3. Execution speed with double precision arithmetic, using floating point variables and mathematical functions, cos, at 2, log, exp, sqrt are the most popular ones. Of double precision as opposed to single precision comes at execution cost. The operations with double precision are usually slower. One area of computing where this is a particular issue is for parallel code running on GPUs. For example, when using NVIDIA's CUDA platform, calculations with double precision are 3 times as slow as with single precision. See also, IEEE standard for floating point arithmetic, extended precision, notes and references.